For years, scientists have been trying to come to terms with a terrifying possibility. What if many of our measurements of the universe are wrong? Not because of faulty instruments or miscalculations, but simply because we might be standing in the worst possible place, right in the middle of a gigantic cosmic void. When we look at the universe from far away, everything appears calm and orderly, an infinite sea of galaxies spread out more or less evenly. But when we zoom in, when we look more closely, that's when we realize how full of enormous holes the universe really is. Imagine the cosmos as a huge city. Some areas are packed with skyscrapers and people, galactic clusters. Other parts are like highways, where galaxies line up in long filaments. And then, there are places that seem completely abandoned. Regions where matter is far sparser than average. Galaxies are much farther apart, and light itself behaves differently. These regions are called voids. Some are just a few tens of millions of light years across. Many are hundreds of millions. But there is one that, if it exists, is several times larger than the entire Milky Way galaxy. And we might be living right inside it. To find voids, astronomers do something very similar to creating a 3D map of a giant city. You record the position of every building, measure distances, and when you put it all together, you get a complete picture. That's exactly what they do with the universe. Billions of points of light are recorded, each point a galaxy. Using precise distance measurements from their light, scientists figure out exactly where each galaxy is, how far away it is, and how fast it's moving away from us. When these maps are completed, something strange appears. The universe looks like a gigantic cosmic web, full of knots, filaments, and clusters in some places, and stretched out empty regions in others. These maps have been produced by massive projects like SDSS, DES, DESI, and Euclid, each one more accurate than the last. And the more precise the data became, the clearer it got. Matter in the universe is not uniformly distributed. Large parts of it are almost empty. Voids aren't just empty space. They actually alter space-time itself. Let me give you an analogy. Imagine you're driving on a crowded highway. Traffic everywhere, you're moving slowly. Then suddenly you enter a wide open, empty freeway. Everything opens up. You speed up. The journey feels easier. Exactly the same thing happens to light inside a void. When light travels through a low-density region, the different curvature of spacetime, plus an effect called the integrated Sachs-Wolf effect, slightly changes its path and apparent brightness. So, based on this effect, if we happen to be inside a giant cosmic void, it's possible that all the measurements we make about the universe are slightly off. Not by much, just a few percent. But in cosmology, a few percent makes a huge difference. And this is where we reach one of the greatest mysteries of modern cosmology, the Hubble Tension. Let me explain it simply. We have two main ways of measuring how fast the universe is expanding. 1. We look at the cosmic microwave background, the light left over from the earliest moments after the Big Bang. 2. We look at nearby exploding stars, supernovae, and other distance markers. Both methods measure the expansion rate, but they give different numbers. One says approximately 67 kilometers per second per megaparsec. The other says approximately 73 kilometers per second per megaparsec. That's a huge discrepancy for cosmologists. For years, they thought it was measurement error. But as instruments got better, the disagreement stayed. This means one of two things. Either our physics is wrong, or we're in a special location. 2013. 3 researchers, Keenan, Barger, and Cowie, decided to do something simple: map the galaxies in our cosmic neighborhood. Not the whole universe, just our local area. Something that had been done hundreds of times before. But this time, something was different. When they put the data together and built the 3D map, they found a strange pattern. The number of galaxies nearby was much lower than expected. The farther out they looked, the denser it became, as if they were moving from the center of a void toward its walls. When they finished the calculations and estimated the size of this underdense region, the number was staggering: 1.5 to 2 billion light-years across, several times larger than the entire Milky Way. And we were right in the middle of it. They named it the KBC Void, after their initials. For several years, the idea exploded. Scientific papers, conferences, heated debates. Because if this was real, a huge chunk of the Hubble tension could be explained. But there's always a but. Starting around 2020, newer and larger datasets began arriving. DESI, one of the largest cosmic mapping projects ever, released results in 2024. Euclid, the European Space Telescope, sent its first data in 2025. When scientists compared these new datasets with the KBC claim, things didn't match up. If a void that huge existed, with 20 to 30% lower density, it should have been blatantly obvious in the new maps. But it wasn't. New calculations showed that any local underdensity, if it exists, is much smaller and shallower, at most 10 to 15% lower density. That could explain maybe 10 to 20% of the Hubble tension. Not all of it. So after all this, where are we now? Are we inside a cosmic void? Simple answer, we don't know. More nuanced answer, maybe, but not the way we once thought. There might be a slight local underdensity. It might affect our measurements a little. But that gigantic 2 billion light-year void? Most likely it doesn't exist. The Hubble tension remains a mystery. Most researchers believe the real explanation lies elsewhere. Perhaps dark energy behaves differently than we think. Perhaps dark matter has hidden properties. Perhaps even general relativity needs tweaking. Or maybe we simply haven't figured out how to measure correctly yet. Our local universe might indeed be slightly less dense than the cosmic average. That slight underdensity could explain part of the expansion rate discrepancy. But none of the current evidence supports the idea that we live in a giant, unusual void. That means the real problem, the Hubble tension, is still there, and it probably won't be solved with a simple "we're in a special place" explanation. Current evidence suggests our local region may be slightly underdense, but that small underdensity cannot resolve the Hubble tension. Therefore, the issue is likely deeper and will require new physics or major revisions to our models. Ongoing projects like DESI, Euclid, and James Webb will deliver more data in the coming years, making answers clearer. The question, "Are we in a special place?" remains scientifically open, but the evidence today suggests no. Our location is far more ordinary than we feared a decade ago. And that very ordinariness actually helps us measure the universe more accurately, test our models without location bias, and understand the cosmos better. Thank you for watching Astreyon. What do you think is causing the Hubble tension? Let me know in the comments.